welcome back to another video. In this video, I will be talking about maximums and minimums of functions in higher dimensions. Now, in this case scenario, we will be talking about a function f which has two inputs, x and y, and has just the output f. So this particular function maps from R2 through the function f goes to just R1. Now, let's look at our region that we are bounding this over. So our region that we are bounding this over is just x squared plus y squared is less than or equal to 4. So essentially we are looking at a function that looks like this over a circle of radius 2. So we have this is our input plane. Anything that is inside of here can be inputted into our function, where this is y, this is x, this is 2, 2, this, I should say 2 comma 0, 0 comma 2, this would be negative 2 comma 0, and then this would be 0 comma negative 2. And we are looking for maximums and minimums of this function in this plane. So, first off, let's look at our formula that we know from Calculus 1 or Calculus 2. So our formula tells us that if we have a function y and x, a y of x that is like this, from a to b as our constraints rather than our three-dimensional, then we must look at the endpoints over here and at a point where the derivative of the function, the rate of change, is equal to 0 to find our relative max and mins in this domain, or our absolute maxes and mins. So we will be, this is assuming f is continuous, by the way. So we have to plug in f of a, f of b, and let's say that this point is just c, so we have to plug in f of c as well. And we must plug all them in to find our maximum and minimum values. Now, let's look at our function that we have today. So it looks something like this, where you have that they all go down. So as you can see, it looks kind of like the following, where our boundary curve of f looks like that. So this is at the point, this is over the circle, x squared plus y squared is equal to 4. So that is important for our boundary critical points. But first off, let's look for our interior critical points, which we could assume is just going to be right here, as this is a minimum. Now, these interior critical points occur at points where the gradient of the function f is equal to the 0 vector. So what this means is that gradient f equals 0 vector, and this is of x and y. So this means that the partial derivative of f with respect to x is equal to 0, and the partial derivative of f with respect to y must be equal to 0, as this means that the direction of greatest change is just staying still, as the direction of maximum increase is just the direction of the gradient vector. So, what this tells us is, for our equation, our critical value must follow these two cases, and as you can see, our gradient is just going to be our partial derivative with respect to x, which is going to give us 2x, and with respect to y will give us 4y, and that is equal to 0, 0. So this tells us that 2x is equal to 0 and 4y is equal to 0. So this is quite clear that our point is just 0, 0. So this is our first critical point, which I will label over here as an interior critical point. So this is 0, 0. Now let's look at our boundaries. So we have this surface right here, and we are integrating over this surface. Now, for our function, x squared plus y squared equals 4, or our boundary, we can imagine this as a level set of the function g of x comma y is equal to x squared plus y squared. So that is that this is a level set. So what this tells us is that at any point our gradient is just pointing, here I'll draw this better, our gradient is normal to our function. So our gradient is pointing perpendicular to our function, as you can see. Now, for our function f, which has this surface, let's say that we have a point like this over here and a point like that over here, we can imagine that right here, the movement of the function is only this way, so our gradient of f is in the same direction as our gradient of g at this point right here. So how do we say that things are in the same direction? Well, we say that they are parallel, which means that the gradient of f is equal to a constant, which we will call lambda, which is our Lagrange multiplier, times our gradient of g. And this is of x and y, and this is of x and y. So since these are pointing in the same direction, this equation can be used to find them, along with the original equation, which is just g of x and y is equal to 4. So this will give us a system of 3 equations in this case, which we can use to find our critical points on this function. So let's look. So our gradient of f, as we remembered, is just 2x, as we say over there, and then 4y. And our gradient of g, which is being multiplied with lambda, which we can actually just go ahead and move on the inside, is just going to be the partial derivative of this with respect to x, which is just 2x, and this is lambda 2y as well. Oops, that was very messy. So this is equal to 2 lambda x and 2 lambda y. Now, if 2x is equal to 2 lambda x, as we see in our first equation, and 2y is equal to 2 lambda y, then we can do the following. We can subtract 2 lambda x from both sides and we get 2x, or we could just divide both sides by 2 first, and then we just get x minus lambda x is equal to 0, and then we can factor out a 0 from this, and we get x times 1 minus lambda is equal to 0, which tells us that for case 1, x is equal to 0. So if x is equal to 0, then we can check that with our original equation, x squared plus y squared is equal to 4. So we can plug that in, and we get x squared, which is 0 squared, plus y squared is equal to 4, which means that y is equal to plus or minus 2. So this gives us 2 points right here for our exterior points. So let's write this over here. So this tells us that there's a point at 0, 2, and a point at 0, -2. Now, let's use our case 2, which is that 1 minus lambda is equal to 0, which means lambda equals 1. So if lambda equals 1, then 2y, or then this means that this is supposed to be 4y, then 4y is equal to 2y, as our lambda right here was 1, which means that let's divide both sides by 2, this means that 2y minus y equals 0, which is only the case when y is equal to 0. So for our case 2, this implies that y equals 0. So now we can use our original equation g, which was x squared plus y squared, and y is equal to 0, equals 4. And this tells us that x is equal to plus or minus 2 as well. So we have 2 more points that we have gotten right here, which is 2, 0, and -2, 0. So these are all 5 of our critical points. We have 0, 0, 0, 2, 0, -2, 2, 0, and -2, 0. So now we can see quite obviously through this that this is just going to equal 0, which is going to be our minimum of the function, as everything else will return a positive value. So this is our minimum, and that is at 0. F is equal to 0. Then we can also see that since the 2y squared has this multiplier of 2 making it larger, that the points that have a y value are going to be our maximums as they are multiplied by 2. So what this tells us is that these two will be our maximum, and since this is, oops, I actually went through it, since this is at our 2 comma negative 2, this is going to be 2 times our 2 squared, which is 4, which is going to equal to 8. So this will be our max at 8. So for our two answers, we have a maximum at 0, comma 0 of, or no, a minimum, sorry, of 0 and a maximum at negative, or at 0, comma 2 and 0, comma negative 2 of 8. So this is our answer right here. So anyway, I hope that you all enjoyed this video. I hope that you learned a lot, and thank you so much for watching. Please like and subscribe.